Okay, in this lesson we're going to review the effect of material properties on the way materials behave and fail. So first let's talk about ductility. Ductility is the ability to deform before the material breaks. So how much deformation is allowed before we consider something to be ductile? So the industry standard has been to say if materials allow more than a 5% elongation, then we're going to consider them ductile. And that means if they're less than 5% elongation when they fracture, we'll consider them brittle. So here's an example of a material that is ductile and was stressed until failure. And you can see a couple things about it. First off, you can see that the diameter very obviously changed. There was definitely an elongation that occurred before the material actually fractured. Also, and we'll come back to this several lessons from now, but notice that there's a 45-degree angle, or nearly a 45-degree angle along the fracture line. So that's kind of an interesting property of ductile materials. They appear to fracture 45 degrees away from the normal stress, which makes us think something about the shear stress might be what actually caused the failure. So here's a good time to remind ourselves that although we're only applying normal stress, the individual elements within the part exhibit not just normal stress but also shear stress in the 45-degree plane away from the normal stress. Here is a brittle material that was stressed until failure. Notice there's not very much elongation. Matter of fact, we really can't see any elongation. And also notice that the shear, that the fracture appears to be 90 degrees. It's pretty much a horizontal line. So that also tells us some interesting things. That there's definitely a difference in the way ductile and brittle materials fail. We're going to consider materials to be even if they exhibit the same characteristics in tension or compression. So here's a ductile material that was put in compression. Notice that we really can't say that the ductile material failed. All we can really say is that it's deformed so much that it's probably not useful as it originally was. The brittle material definitely did fail. Notice there's not a lot of change. We can actually see a little exhibiting of buckling. And again, what's really interesting about this failure line is now this failure line seems to be on the 45 degree. So we'll spend quite a bit of time talking about failure mechanisms. But I just want you, as we're looking at these pictures, to start considering more than just that it failed or even what shape, but start thinking about maybe why it failed on 45-degree axis in compression, 90 degrees in tension. It doesn't fail in compression, although this is no longer a useful part, I don't think, and failed 45 degrees in tension. So we've discussed what happens with normal stresses. Let's consider what happens with shear stresses. So again, we have a ductile material. Notice this white line that was painted straight across has now wound around 3 times before the failure occurs, and now the failure is 90 degrees. Whereas the ductile material, whereas the brittle material did not deform even 1 time around, and the failure is now 45 degrees. Also, we ought to introduce this concept of the modulus of rigidity. We've already talked about it a little bit in the last lesson. So there's this constant G that has something to do with the torsional stress, or the shear stress that's being induced, and the angle that the material actually goes. And again, this is a material property. This changes whether it's made out of cheese or steel. Solving for G, notice we have 3 material properties. We have E, which is the modulus of elasticity, the modulus of rigidity, and Poisson's ratio. And this is a fairly well-established relationship. If I have any 2 of these elements, then I can calculate the third one. So let's talk about when we apply so much shear stress to the material that it actually fails. Before we talked about stresses, we would talk about force divided by area. Now we're talking about force times a distance, or a torque, times the distance again. So it's kind of like force times distance squared, and we need to have the same units of force over area. So now we're going to introduce this J that has something to do with the area of the object that's being rotated. And we'll come back and talk a little bit more about this in detail as we start doing some examples. But it turns out that the ultimate shear strength is actually related to the ultimate tensile strength in ductile materials. So that's a really interesting quality. We'll talk about this a lot in class, but I want to go ahead and mention that a lot of the theory for failure analysis is empirically driven. In other words, there isn't really a mathematical model for why this is a case. Instead, there's a lot of experiential evidence that demonstrates this definitely is the case. Okay? So let me give you just a little bit of notation. All three of these symbols have units of force divided by area. So let's talk a little bit about what we mean. When we talk about sigma, we're talking about normal stresses in a part. When we talk about tau, we're talking about shear stresses. And when we use S, we're talking about strength of the material. And the biggest way to help you understand why we're differentiating between an S and a sigma, and we're not just carrying one symbol all the way around, S has something to do with the strength of the material. It's a quality of the way the part was made, the material of the part. Sigma and tau have something to do with the loading conditions. It's a quality of the types of forces and the location of the forces on the part. So that's a very big difference. These are, so here's some example. Here's the ultimate tensile strength of material. We'll denote it SUT. This is what we expect the material, this is how we expect the material to behave. In contrast, and also this is the ultimate shear strength. This is what we expect, how do we expect the material to behave. This bottom one, this is the normal direction, this is the stress induced in the normal direction of a given part with a given loading condition, and that's the important part. This is completely dependent on the loading condition. And what we'll find is that if the loading condition causes the stress to be larger than the strength, then we should expect failure. Okay, let's take a look now at another type of material property, hardness. And one of the major things we're trying to do with hardness is come up with some sort of standard so we can compare two types of material. Now, maybe a working definition of hardness is the ability of a material to not wear. Very often hardness is tied into whether a material is brittle. So turns out that typically harder materials are more brittle, although the definitions of both of those are very different. It turns out that's the way it works. And there's three major types of tests. One of them is the Brinell test. That one has a very specific way of testing. You take a 10 millimeter hardened steel ball, and then you apply either a 500 kilogram or a 3,000 kilogram load, depending on the type of test. And then you measure the diameter of how far that steel ball drove into whatever you were loading it. So you take your specimen, you put this hardened 10 millimeter ball on it, you push that ball with 500 or 3,000 kilograms, and then you measure and see how far in it indented. The next test is called a Vickers. Vickers uses a diamond pyramid shape. Okay, so you're doing the same thing. You apply a load to the diamond pyramid, and then you measure the width of the indenture, how wide, how far down did that pyramid drive into the material. And then the Rockwell, which is a very common test, uses a 1/16 inch ball or a 120 degree cone-shaped diamond indenter, and then it measures the depth of penetration. So the top two measure diameter across the surface, where the Rockwell measures the penetration depth. And then there's a translation between the two of them. It turns out that all three of these tests are related to each other. And so here's a way to convert different tests. So if you know the result of one test, then you know what you can do with the other tests. One more topic for the day, we're going to consider the amount of energy that is stored in a part when a part undergoes stress and strain. So here's the definition. Let me explain it. Suppose I have, I'm within the elastic region of a deformation. So we've applied a stress and there is strain. It turns out that the area under this curve is the amount of energy in that energy density. So that's the amount of energy contained in that infinitesimally small part. At the elastic boundary, this is just a triangle, so it's just the yield stress, the yield strain divided by 2. That's the area under this curve, and that's the amount of energy density. If I want to find out how much energy is actually under there, I would need to integrate that over the entire volume. So for example, if we have a cylinder that's been stretched to the elastic limit, this is the same for every element within the volume. So in other words, this U0 is a constant throughout the entire volume. So here's the volume, pi r squared times the length is the volume, multiplied by the density. This is the amount of energy. So here's my question for you, and we'll talk about this in class. How can we use this energy relationship to say, let's say we want to use a cylinder, we want it to function like a spring. So think about how this energy could cause that. Finally, last topic for the day, we're going to talk about fatigue. Fatigue has to do when we take a part and we stress it and we alleviate the stress and then we stress it again. We do that time after time. Probably everyone at some point has taken something like a paper clip and broken it in half by bending it back and forth over time. So we know that that fatigue exists and that it's a big problem. If we graph what happens, here is a log scale showing 1,000,000 cycles, and it's showing that some materials will continue to fail forever, will continue to get weaker forever, whereas other materials, after a certain point of time, they'll no longer get weaker. So we'll say that there exists an endurance limit for some materials, while some materials don't have an endurance limit. We'll talk about this in great detail throughout the semester, but just as an introduction to the concept, I wanted to lay it out for us today.